Thank you so much for having me. Thank you to the organizers for organizing what is probably one of the best conferences I've been to. It is absolutely lovely to be here. I will be talking about some ongoing work on time series ensembling, trajectory ensembling, together with Alex Alemi, Vignesh Birodkar, Hossein Mobahi, and Surab Singh, who are all my colleagues in the perception team at Google Research in Mountain View. But before we delve into ensembling, I will mention something about me. I am extremely happy to be in Gothenburg. I am born and raised on Öckerö in the Northern Archipelago, about an hour from here. I studied engineering physics at Chalmers and graduated in 2011. And after that, I did my Ph.D. also at Chalmers in theoretical physics. And I spent over 5 years as a postdoc studying string theory and black holes and all those fun things. But when I ended up at Stanford in 2018, I started to miss numbers. Spent a lot of time with pen and paper, and I started noticing that everyone around me were talking about machine learning. And of course, if you're at Stanford, I sat in on Andrew Ng's lectures and then built my first cat versus dog classifier, and that was lovely, and I was hooked. So I joined Google in early 2020 in their AI residency program out of, I'm based in Mountain View. I have seen the office a total of 5 times or something like that, so I'm really based out of my basement. But this week we're going back to the office, so next week I'm going back, and it will be so much fun to see everyone. So now, ensembles. So first off, I want to start with some intuition from a schematic image of the loss landscape. So this illustrates a 2-dimensional slice of the much higher dimensional loss landscape that we have when training a machine learning model. And you initialize your model, you end up somewhere in this loss landscape. And this is here illustrated by the little black dots. And then the traditional way of training is through some version of stochastic gradient descent, possibly with some momentum. So you end up with like a little wiggly line going into some valley of the loss landscape, at least in this 2-dimensional slice. Now, traditionally, ensembles basically means, we had some font issues here, so there might be some formatting things with the slides. Traditionally, ensembling means that you take your endpoint of these several training runs, of these ends of these yellow lines, and you average their predictions in some way. And this really helps by correctly classifying harder samples of your data set. It has more advantages than that, but that is the one that is easiest to understand. And to see this, let's revisit the toy model dog versus cat classifier, where in this toy example, our ensemble consists of 3 models. So say model 1 here gets a sample in, and it says I think this is a dog. With 55% probability, this is a dog. So I'm going to classify it as a dog, even though it's a 45% chance of it being a cat. Model 2 says tricky, but I think it's a dog. 51% chance it's a dog, 49% it's a cat. So again, classify it as a dog. Whereas model 3 in this ensemble might say, no, I'm pretty sure it's a cat. 70% chance it's a cat. And so by averaging these predictions in probability space here, the ensemble might correctly classify this sample as a cat. The big downside of this is that these ensembles are computationally expensive. In this case, it took 3 times the amount of training compute to actually train this ensemble. And they're also more expensive at eval time. But the big cost lies in training. And this is where we chose to focus. So we started with the question, what if we can use just one training trajectory and see similar results. And this is very appealing because there's a lot of data accumulated during training. Standardly, you checkpoint at some places during training. You have way more data accessible than just the final model. So what if we could just use these things, ensemble them, and see performance gains? Well, here be dragons, because models during one training run are sort of similar to each other. And if you're not careful, you might have very similar models, averaging their predictions, and averaging predictions of just very similar models. All you did was up your cost at eval time. You don't really see any gains from that. So before we proceed, I want to mention some related works and caveats. So first of all, ensembling generally is more general than what I just described. It is not constrained to just using the same model architecture. You can combine predictions from transformers with convnets, whatever you want. But for simplicity here, we are looking at ensembles of the same model architectures. Also, there's a bunch of related works on these. These ideas are not new. There are great works on maintaining running averages of the weights that have been shown to be very beneficial, for example, in the context of semi-supervised learning. There are other works where one modifies the training trajectory in some way. For example, train for a while until you end up in a local minima, bump up the learning rate, keep training until you hit another local minima, and repeat this process, and then ensemble the checkpoints from the various local minima. But what we're looking at here is not modifying our training at all. And we are looking at ways of reducing costs at training time. Now, we can also use this in combinations with dropout and other means of regularizations, or like stochastic methods. So why might this be useful? Well, this is also, you could think of this related to something called spectral bias, which says that neural networks learn different kinds of features at different times in training, where you learn large-scale features early on, and as training goes on, you learn more and more fine-grained features. And different kinds of these features might be useful for certain samples and certain tasks. We can also get some motivation from thinking about certain tasks, such as fine-tuning, which I will talk a lot more about later, where you start from a pre-trained model, so that contains some important information already, and is very sensitive to choice of hyperparameters. And there are issues with catastrophic forgetting that can happen if you're not careful with how you tune these hyperparameters, where you just forget all of the important knowledge that is contained in this original pre-trained model. And so early checkpoints actually contain important information as well. So we have now, okay, this might be a good idea, so let's try it. Then how do we average these predictions? There are a bunch of ways you can do it. We tried several different ones. What we found seems most promising is averaging them in probability space. So we're averaging probabilities from different checkpoints. But then how do we average these probabilities? Well, we could just do a plain average, the simplest you could do, just units weights for them all. We could have some ad hoc thing where we say later models are probably more likely to be correct, so let's weight them higher. We could hold out a small data set at train time and then weight them by the likelihood of them being correct as measured on this small held out training set. And we could also hold out a small data set at train time to use to compute like the best weights in a least squared sense. And notice that this data set can be pretty small because all we're doing is fitting order of magnitude 10 weights to it. So we don't need huge amounts of data for that. So we did an experiment, a very simple experiment on this. We took a standard model. We took a wide ResNet 2810. We trained it on CFAR 100 by the standard ways it is done in the wide ResNet paper. And we saved 500 images for computing optimal weights. This is trained for 200 epochs. And if we take checkpoints accumulated from the 50 last epochs, and we ensemble 10 of them, we see no gains, really regardless of how we pick the weights. If we go way further back in training, from the last 125 epochs, so more than halfway through training, we do see some gains. And they're all about the same thing for all of these different kinds of weights. So it doesn't seem to matter really at all how you average them. And one way to think about that is that in some way, there's a natural suppression of scale happening between very early models, where the model basically is very unsure and has close to random outputs, where each of the predictions would be roughly proportional to 1 over number of classes, versus later models where the model is pretty confident in its predictions. So even if you have them all weighted the same, when you average up probabilities, the early unsure models have a much lower prediction scores. This is just a schematic way of thinking about why this might make sense. So if we can see some small gains of something like a CFAR training, can we use this to get like a better ImageNet benchmark? And it turns out that no, it's not really useful in the case where you have lots of labeled data and finely tuned hyperparameters, such as is the case for like ResNet 50 on ImageNet. In this case, models don't really move that much when you train. If you have poorly tuned hyperparameters, you will see big gains from this technique, however. And cases that are sensitive to hyperparameters might be a good candidate for seeing gains. So let's move to fine-tuning. This is much closer to real-world problems since labeled data is expensive. And so in the lots of situations, we don't have that much labeled data from the particular distribution we are interested in. One good way of doing this is through transfer learning, where you take a pre-trained model on some large data set. In our case, if we're doing image classification, standard is a model pre-trained on ImageNet, for example. And then you take this model, train it for a few rounds on your much smaller data set, and then use that. The problem is here, what is a few rounds? These settings are very sensitive to number of train steps and learning rates, for example. So in good situations, you want this to happen. You want your validation loss, here plotted as a blue curve, to follow the trend of your training loss, here plotted as a red curve, in this toy example of classifying circles versus rhomboids. So this is what you want to happen. The model comes up with some classifier, and both losses follow the same trends. But what if it doesn't? In many situations, you can end up in something like this, where the model overfits and it stops learning useful information. This is very easy to slip into when you do fine-tuning because your data sets are so small. So a real-world problem, then, is real-world. A fine-tuning benchmark that we chose to look at, it comes from the VTAB Lightweight benchmark. This stands for Visual Task Adaptation Benchmark. And we're looking at their lightweight sweeps, meaning we are probing 2 different numbers of steps and 2 different initial learning rates. Now, learning rate here decays in a stepwise decaying scheme that we will see more of on the next slide. But the way this benchmark works is that you have a three-way split of your data set. So all of these data sets have a train, a test, and a validation split. You start by training your model on the train set with all of these 4 hyperparameter combinations. You pick whatever hyperparameter combination performed the best on the validation set. You retrain using both train and validation as your training data, and you evaluate at the test set. So in this way, VTAB lightweight on a data set called SUN 397 reaches an accuracy of about 70.7%. This data set, SUN 397, consists of a fairly large amount of images, but it has 397 classes, and it's of a distribution that is different from ImageNet. If you add in data augmentation to this VTAB scheme, which is done in newer versions of it, though not in the original paper, you bump up your accuracy a little bit. So you end up at 72.3. And if you form a checkpoint ensemble, which I will talk more about how exactly we chose which checkpoint to include in it in the next slide, we see gains of over 1% in this case, over current benchmarks. How do we then pick this best ensemble? Well, these are validation loss curves and validation accuracies from one of these training runs. So in general, they look like this, where they first go down, they have a global minima quite early on in training, and then they start going up. Sometimes they can have a second decay, little minima. That is related to one of these stepwise learning rate decays. And it turns out it won't matter much for us. The accuracy, however, the validation accuracy, keeps going up. So the algorithm that we have is that first you start by picking the best checkpoint. Now often this comes from one of the checkpoints in the very end, this region 3. So pick that. Decide how many models you want in your ensemble, and sample the other ones of these from this region 1, a window around the global minima in the validation loss. Then do a couple of these things on data trained on the train set, evaluate the ensemble performance on the validation set, pick the best one, retrain on train plus validation, and evaluate that same ensemble with checkpoints from the same epochs on the test set. And that's how we got the numbers on the previous slide here. And we can check this for another kind of data set. The DTD, the descriptive textures data set, is a much smaller data set that is often used for fine-tuning. We can do the same here. And we, again, see gains of over 1% over the VTAB lightweight benchmarks. So, to conclude, trajectory ensembling can improve existing fine-tuning benchmarks. It is useful in cases where you do see these early global minimas in the validation loss, and we will publish more details about exactly how this works in an upcoming paper. Cleverly choosing the weights of your ensemble doesn't actually help that much. It is fine to use just unit weights. It simplifies life, and you don't have to hold out any data from your validation set or from your training data. And these trajectory ensembles offers an efficient way of preserving knowledge from these pre-trained models, as well as using models that have been heavily fine-tuned to the particular task you're interested in. Thank you so much, and I am very happy to answer any questions you might have.